So there was a problem in the last class in the proof of spectral mapping theorem. So someone pointed out. Who pointed out? So you are hearing me. So we were so spectral mapping theorem. Let's recall the proof again. Okay. Actually, what I said was not correct, and the proof in the book is correct. It is just a slight change we'll do. Okay. So we want to prove the following. So this is the proposition. If P is a polynomial, P is a and X is in some Banach algebra, A is in Banach algebra, then sigma of P of X. If you have a polynomial, then you can substitute in the variable the operator X, and you get another operator. Okay, you can talk about powers of X, and you can get a polynomial in the operators, and then you get another operator. So the spectrum of P of X is same as P of sigma of X. Okay, this is what we want to prove. So for the proof, you take P of Z. It's a complex polynomial with complex coefficient. So let lambda be something in C. Then P of Z minus lambda, you can write it as n equal to 1 to n, some constant, some constant will be there, which is the coefficient, the leading coefficient, the coefficient of highest power, times Z minus lambda I. You can write it like this. For some lambda I, you can write any polynomial like this. Then P of X. This implies, because it's a homomorphism, P of X minus lambda will look like this. Okay. X minus lambda. Okay. So this is true for the operator also. This is true. So now if I want to suppose lambda is in sigma of P of X. Okay. Lambda is not in sigma of P of X. I said that lambda, I use the argument that lambda is in rho of P of X. It's the same thing as lambda is not in sigma. The last step, there is a slight difference. That's all. If lambda is not in sigma of P of X, okay, that means P of X, this is equivalent to saying this means this is in the rho of X. This is equivalent to saying, this is the same thing as saying P of X minus lambda is not invertible. This is equivalent to saying all those, the product X minus lambda is not invertible for all I. Okay. This is clear. These things are clear. But then this is equivalent to saying lambda, this is same as saying lambda i's are not in sigma of X for all I. Okay. For all I. So here, this is equivalent to saying lambda is not in P of sigma. This is true. But what I said is the other way. This is equivalent to saying lambda is in P of rho of X. I said that is not true. That's all. So this is true. Lambda is not in P of sigma of X. This is clear. If lambda I is not in sigma of X, that means on sigma of X, this polynomial does not vanish. So P of X cannot be equal to lambda. P of Z cannot be equal to lambda for all Z in the sigma of X. So lambda is not in P of sigma of X. And the same way, the other way is also true. It's the same argument. Okay. This is fine. Whoever asked this question? Who asked this question? Hello, is there anyone there?
I think he is not here.
I think it was Divya, but he's not.
Okay, it was Divya. So it's a good question. So I said that this is same as saying this is not equal to this is not equal to P of rho of X complement. This is not true. So actually I was confused when I was proving it, but then I thought it's okay, but it's not okay. Okay, so if you remember, or if you look at the video, it will be clear that I was confused. So that is not, but this is true. This is clear. Okay. So this is just direct. Okay, so this is true. So this is actually, this is the proof given in the book. I didn't look at it properly. Okay. So spectral mapping theorem, the proof is fine now. Okay. Now we want to talk about something new. So we have talked about Banach algebras. Now we want to introduce a new object called sigma C-star algebras. Okay. So definition: a C-star algebra A, we again denoted by script A, is a Banach algebra together with what is called an operation called involution, with an involution. As I said, whenever we introduce new operation, it should be consistent with the, it should, I mean, it should behave nicely with the other operations we have already introduced. So involution star, it's an operation A to A, which takes X to X star, okay, such that these things are true. One, it's the antilinear. Okay, all of you know what is conjugate linear, antilinear or conjugate linear. That is alpha x plus y star equal to alpha bar. It's same thing, satisfies the same properties of adjoint. Okay, but here it's just an abstract C-star algebra. So when we take the C-star algebra of B of H, then it is just the adjoint operation. That's what we will take. Okay, alpha bar x star plus y star to x star star is x. It's invertible and its inverse is same as the same involution. Third thing is xy star equal to y star x star. And the fourth one, this is what is the important thing. This is what is called C star identity. So this also, I mean, this is the identity which links the involution and the norm. Okay? That is, all these things are true for adjoint. We know already. We have proved it for adjoint. So this is just an abstract operation. Okay? X star x equal to norm x square. Okay, this is what is called C star identity. Okay, so any Banach algebra with an involution which satisfies this property is a C star algebra, and we know already the examples are B of H. B of H is a Banach algebra with a norm, and then it satisfies the Banach inequality. Norm st is less than or equal to norm s times norm t. All those things satisfy, and it also satisfies with the adjoint. Okay, adjoint operation. So this is one example. Okay. So we have verified adjoint satisfies all these operations. We have verified in the previous course. So, and second example is C of X, X compact, T2, whatever. I mean, it's a metric, you can take compact metric. You will take compact. We will be considering compact subspaces of C and R. Okay, that's what we will be considering in this course. Okay, so these things are not, I mean, whether it is T2 or all those topological things are not really important. So here, so this is a Banach algebra. We know already that this is a Banach algebra. So further, this the involution I have to say F star. We can say that this is equal to F bar. You take just the bar. Okay. So this is I mean, then you know that norm F square, F bar square, which is F star F is just. I mean, you have to verify the property. So which is just mod F square. Mod F square equal to F bar F. Okay, this is just equal to, which is same as norm F square. It's direct. Okay, so it satisfies the C star identity. So third, you can, I mean, there is no different. The third is not a different example. It is just a slightly extended example. So you have a X be a measure space. Okay. X mu. I mean, there's a sigma algebra. I'm not writing that. X mu is a. We can. I mean, as I said, we will be considering compact subsets of R and C. That's what we will be considering. So X may be a finite measure space. We don't need finite measure space, but let us take finite measure space. Then L infinity X mu is a C star algebra. Okay, with the L infinity norm. Okay, and the involution F star equal to F bar, the same F bar. Okay. In fact, we will see that in some sense, this L infinity is a closure of C of X. in a different topology. Okay, if you take the almost everywhere convergence with some property, I mean with some condition, it is a closure. This L infinity is a closure of C of x. If you consider as operators, C of x can be considered as operators on L2. Okay, as multiplication operator. You can represent C of x as multiplication operator on L2. If you take the closure in the strong topology, so the C of x is closed complete with respect to norm topology, and the operator norm of C of x, operator norm of a continuous function, operator norm of the multiplication operator with C with in C of x coincides with the infinity norm. We will see that again. Infinity norm. Well, it will not coincide. It depends on the measure. Okay? I mean, in the Lebesgue measure case, we have seen that it coincides. Okay. So when the measure is faithful, it will coincide. I mean, there will be when the measure is nice, it will coincide. But it's a nice operator. But if you take the closure of that, you will get precisely the L infinity. What I'm saying, we will be. I mean, I say this, but we will be proving this anyway soon in this class. Okay, so L infinity is another example. Okay. Okay, so this is C-star algebra. So now we want to talk about what we want to talk about is a homomorphism between C-star algebras. In particular,
sir, is it true that B of x is a C-star algebra if and only if x is a Hilbert space?
What do you mean by? I mean, if it's an inner product space, you are asking.
No, like I mean, so what I'm asking is that if x is a Banach space, then can B of x be given a C-star algebra structure?
How will you give? I mean,
I mean, that's what I'm asking. Like, can it be given?
No, it depends. I don't think so, but I don't see any such theorem. I am not.
Like, do you have any reference? Like, because actually I thought of this problem few days back, but I didn't get any satisfactory answer. That's why I was asking.
No. I see. We say that if you take L1, it's a Banach space. It is a Banach algebra. You can give an involution on that, which is the inverse, using the inverse and other thing, you can give an involution. But then it will not satisfy the C-star identity. So, so on a B of something, how do you give? That is the problem. I mean,
that's the thing. But
then I think it has to be a Hilbert space, but I don't know the proof. I don't know. I'm not sure. Okay.
I mean, is there any general trick which can actually help you answer when a given Banach algebra can be given a C-star algebra structure by
the point is, if you have any C-star algebra, then you can represent it on a B of H as a subalgebra, as a closed sub. I mean, say I have given an example. B of H is a C-star algebra. You can take any S. Okay, let me give an example. You take any S contained in B of H. Okay. Then you take the span, I mean, then you take products of S and S star. You can take the C-star algebra generated by S. Okay. I mean, the B of H is a bigger C-star algebra. You can take the intersection of all C-star algebra. Then you can indeed talk about C-star of S. C-star algebra generated by any set. Okay. So this will be a norm-closed C-star subalgebra of B of H. Okay. But in gen, so there are many C-star algebra. So there are many C-star algebra. But there is a theorem, JNS construction, which says that any C-star algebra can be represented like that. So it's any C-star algebra is actually a norm-closed subalgebra of B of H. Okay. So C-star can always be represented like that. So I don't know whether you have a Banach. What do you mean by if you take something on a Banach space? So if you have a C-star algebra, then you can actually represent it in a B of H.
So like, is this true that if B of x can be thought of as a closed subalgebra of B of some y, then x can be thought of as a subspace of y or something like that?
It is not clear why. I mean, what do you mean by that? B of k is some subspace of B of h, you want to say. Okay, BK is the Banach space. Okay.
Like then can K be thought of as a isometric to a subspace of H or something like that? Then that answers.
What is the way to define an inner product? Okay. Unless you have some more conditions.
Yeah, that was what I was thinking, but I didn't get any idea.
No, it should be you want to say it is always something contained in that. You want to say this is equal to B of H. That need not be true for any C-star algebra.
No. What I'm saying is that BK is subset of B of H. Like, does that imply that A is.
You need more condition on the involution. You have to say something. If you consider some particular example, then you may be able to say. Okay, I mean the involution is actually some sort of uniqueness is there, but you have to say what is that involution. See, if you have an involution, then that I think that will coincide. The involution is determined by the sister algebra. But still, how will you get this is same as some B of H1 or something where H1 is something contained in H or something. I don't see any reason. I don't see anything like that. Okay. You can try this. Okay. You can try to prove it. At least I haven't encountered this. I haven't thought about it. Okay. Okay. So anyway, that's not our interest. Our interest is to prove spectral theorem. In fact, we are not even studying C-star algebra. We are only studying C-star algebra. It's a tool for us to prove something. Okay. So where are we? We want to talk about representation of C-star algebra. So this is representation. A representation is nothing but a homomorphism, but it should preserve all the algebraic operation. Okay. Homomorphism is something which preserves algebraic operation. We say it's an isomorphism if it preserves if it is bijective. But then the point is in a C-star algebra, norm will be automatically preserved if it is an isomorphism. In fact, we will prove immediately after this definition, we will prove that any representation is contractive. Okay, it's automatically continuous. In fact, the norm is less than or equal to 1. Okay, the norm of the representation. Okay, now representation is a linear map, so its norm is less than or equal to 1. So if it has an inverse, then it should be equal to 1 because the inverse is also a homomorphism. That should also be less than or equal to 1. So it should be isometric. Okay. Okay. So definition. What's the definition? A B a C-star algebra. A representation by a representation of C-star algebra of A is a homomorphism by from A to B of H for some H, for some Hilbert space, H. And it's a homomorphism. By homomorphism, we mean it's something more than a homomorphism. Is a star homomorphism. Okay? That means it satisfies all these properties. Pi of xy equal to pi of x times pi of y. So pi, you have x in A, pi of x is an operator in B of H. Okay, you represent the C-star algebra as operators on B of H. Then pi of xy equal to pi of x times pi of y. And pi of x star equal to pi of x star. Here the star is adjoint. The star of the operator is adjoint. That's all. Okay, it's a linear map, of course. It's a homomorphism. It's algebraic homomorphism. Okay, so it has to be a linear map. It has to, pi is linear if you want. Okay. It's a linear. It preserves the products. It preserves the star. Further, we will be considering only unital star homomorphism. That is pi of. So the thing is, we consider only unital C-star algebras. Okay, we have a C-star algebra. We say a C-star algebra is unital. A is unital if there exists an identity. Okay, 1 in A, identity. Okay. We consider only unital C-star algebras. So pi of 1 has to be 1 here. I mean, this 1 is on the Hilbert's. This is the identity operator. Maybe you can write. Let's use 1. Okay, pi of the 1 is 1. This 1 is on the C-star algebra. 1A equal to 1B of H. So it takes the identity element of the C-star algebra to the identity operators on B of H. So this is what is called a unital star representation, unital star homomorphism. You can consider homomorphism between C-star algebras. Okay. Here it's here by representation we mean the range C-star algebra is B of H. That's all. Okay. So remark: if you have any homomorphism between C-star algebra, this is true. That pi from A1 to A2 be a star. It need not be unital. Star. No, it has to be unital. Then only we can talk about spectrum. So unital Biunital means pi of 1 is 1. Star means it preserves the star. Pi of x star is pi of x star. Star homomorphism, okay, between this. Then norm of pi of x is less than or equal to norm x for all x. Reason, if for lambda in C, okay, if x minus lambda is invertible, I mean, if x is invertible, pi of x is invertible. So x minus lambda is invertible, then pi of x minus lambda is also invertible. But pi of x minus lambda is pi of x minus lambda. By x minus lambda, we mean x minus lambda times 1a, right? That's what it means. So this implies pi of x minus lambda, because it's linear, you can take the lambda out, times 1 b of x, okay, is invertible. Homomorphism means it will take invertible elements to invertible element. Okay, you just write the property of the homomorphism, you will get there. Okay, so I mean, you want to prove something is invertible means S inverse equal S inverse S equal to identity. So pi of S inverse, you will get that will also form, that will be satisfy the inverse property. So it is invertible. Pi of x minus lambda is also invertible. Okay, so this implies rho of this implies what? So rho of x, if we have a lambda in rho of x, then lambda is in pi of rho of x. So rho of pi of x, right? If you have lambda in rho of x, that's what it means by x minus lambda is invertible. That means pi of x minus lambda is also invertible, means lambda is in rho of pi of x, right? So this implies sigma of pi of x, the complement is contained in sigma of rho of x. Okay. So this implies r of pi of x, the spectral radius, it has to be less than or equal to r of rho of x, the spectral radius. So if x is normal, that is, if I mean, we can talk about normal elements in C-star algebra also. That is x star x equal to x star equal to 1 r. So I proved it for operators, but it is true for, I mean, see, we proved spectral radius formula for a general Banach space. Then for any normal element, you can prove this using the C-star identity. You can prove that x power 2 power n, that thing you can prove, or at least for self-adjoint elements you can prove. Okay. Then norm x, if x is normal, then norm x equal to r of x. Okay. This is true for C-star algebra also, not just for B of x. Okay. So then this implies pi of x, norm of pi of x is less than or equal to norm x. In particular, this is true for self-adjoint elements. Self-adjoint elements are, I mean, x equal to x star. So x certainly commutes with x star. Okay. So now, for any x in A, pi of x star x pi of x norm square equal to pi of x star pi of x. This is the C-star identity. But then that is same as pi of x star x because it's a homomorphism. Okay. But then that is equal to, that is less than, x star x is self-adjoint. Okay. Take the star, it is the self-adjoint. So that is less than or equal to norm x star x. Okay. But that is equal to norm x square. Okay. So norm of pi of x is less than or equal to norm x. Okay. So any homomorphism between C-star algebras are contracting. Okay. 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 So now we want to study the special class of C-star algebras, the commutative C-star algebra, C of x. Okay. C of let's say sigma. Sigma is the notation used there, so let me use it. So first we want to study for a self-adjoint C-star algebra in the sense that, I mean, they are all real value. I mean, the spectrum is real. What I mean is the I mean, for C of sigma, where sigma is contained in real line proposition, we compact. Okay, we take a compact subset of R. Okay, then if you take any operator, you take, I mean, we want to consider, see, first we want to do two things. We want to consider, so you see, we have sigma is a compact subset of R. We want to talk about the, we want to investigate the representation of C of sigma. One way is to define a measure on sigma, and then you talk about the multiplication operator representation. Or we can do, but we want to relate it to some self-adjoint operator or something. So here we take any Hilbert space and take any self-adjoint operator with whose spectrum is contained in this sigma. Then we can define a representation. Okay, that's what we want to do first. Okay, so let H be any Hilbert space, H be a Hilbert space. Okay. And D is in B of H, self-adjoint. So if it is self-adjoint, we have already seen that sigma of T, the spectrum is contained in real. We just proved it, okay? So, such that sigma of T is contained in sigma, okay? Then there exists a unique representation pi from C of this. This is a C-star algebra, C of sigma to B of H. So the uniqueness is determined by that, such that pi of, let me say what is f naught. F naught is a function, f naught equal to t. Pi of f naught equal to t, where f naught of t equal to t for all t. Okay? This is the, I mean, this is in C of this. Okay? This is a function. As a function on sigma f naught of t, this is the identity function. Identity is not the other identity. I mean, the constant function 1 is a identity element of the C-star algebra. This is the identity polynomial. Okay, the identity, or if as a function, it's identity function. So this is different from the identity of the C-star. Okay, so this is one thing. Okay. Conversely, if pi from C of sigma to B of H be any representation, okay, then pi of this f naught is the function, is self-adjoint, such that sigma of pi of f naught is contained in C of this. Okay. Okay. So the proposition is clear. The whole page is the proposition, as you can see, which I will do. So what we are doing is the following. We take a compact subset of real line. Okay. Then we want to consider the representation of C of sigma. Okay. So one way of constructing that representation is you take any self-adjoint element on some B of H, any self-adjoint operator whose spectrum is contained in this sigma. Then you can define a representation by defining pi of f naught equal to t. See, the proof will go like this. You take pi, you define pi of f naught equal to t, then you take polynomials, okay, and then you know how to define the polynomial. Because it's a representation, it has to be a homomorphism. So pi of any polynomial has to be the polynomial of t, polynomial in t, the same polynomial in t. That's what it has to be, okay, because it's a homomorphism. Then you prove that because it's a C-star, because it's a representation, I mean, then you prove that it's contractive, but it's not actually defined on C-star algebra. So you cannot say that it's contractive. Then you have to prove that it's actually bounded. Okay, so you have a representation of the polynomials on this, okay, which is bounded. This representation is bounded. Then you can extend to the whole of C-star algebra. Okay, It's a linear operator which is bounded, so you can extend it, and it will still be a representation. Okay, because multiplication is non-continuous or whatever you will see. So that's the idea. Okay. So the other way is also easy. So let's take the proposition inside. So we are given sigma contained in R, okay, capital sigma contained in R, and we are given a H Hilbert space and T in B of H, self-adjoint, okay, such that sigma of T is contained in C. So then we want to construct a representation. Okay, so we want to construct a representation. So we want to define phi naught from polynomials. This is polynomials in sigma. Okay, polynomials are continuous function. Okay, to B of H. I mean, you have to take f naught. You want f naught going to T. Okay, the identity function T f of T equal to T, f naught of T equal to T, that goes to go to T. Then any polynomial, any P will go to P of T. You have the polynomial, and in the variable, whatever the Z or whatever, here it's a real variable. It's defined on the subset of real line. So in the variable T, small t, you have to substitute the capital T. Okay, you get an operator here. Okay? This is clearly a homomorphism. It's a homomorphism. Okay? It's clearly a homomorphism. All you have to prove that this is contracted. Now, we know T is normal. T is self-adjoint, so it is normal. And we have proved that for normal, this is true. P of T, operator norm, P of T is P, is an infinity norm defined on sigma of T. We have proved in the last class. Okay. So you remember this? Okay. Norm P of T. But then that is less than or equal to norm over sigma. That's a bigger space, bigger set. Okay. Sigma of T is contained in this, so this is true. Okay, so whatever the homomorphism we have defined, that's contracted. Okay. Now define. So this pi naught. So pi naught extends to C of sigma as a homomorphism. It's continuous. So multiplication of operators is continuous. See, if you have Fn converges to F in infinity norm in C of this, okay, and Gn converges to G in this, okay, then pi naught Fn is an operator, pi naught of Gn is an operator. This will converge to pi of F, pi of G, right? Fn converges to F, then pi of Fn will converge to, pi of Fn will converge to pi of F in norm. Okay, pi of Gn will converge to pi of G in norm. That's how we have defined the representation. Okay, then the product will also, it's jointly continuous. The norm is jointly continuous. So it's enough to define it on a dense subspace. Okay, this is fine. Is okay?
Yeah.
Okay, so we defined it on polynomials and then we extended it. Now it's clear that, by definition, pi 0 of f naught is T, and what else we have to prove? We don't have to prove anything. That's all. So but the representation is unique because this f naught generates the algebra. Since f naught generates the algebra C of this representation is unique. This representation is determined by this. It has to be this, pi of f naught equal to T. Right? F naught generates means what? The algebra generated, you take the algebra generated by f naught, which is just the polynomial cell f naught, right? The algebra generated by f naught is f naught and f naught bar, and but this is just f naught and f naught bar. I mean, you take the algebra generated by that. If not, I mean, it's not just, it is just the algebra generated by this, which is the polynomial. Now you just take the, and then you take the closure, okay? And it's uniquely determined by that, okay? If a pi of f naught equal to t, I mean, it is the algebra, it's not just the algebra, it's the C-star algebra is generated by this f naught. By this, what we mean is, you take the algebra generated by f naught, the smallest algebra generated by this f naught. That is just, you have to take the product of f naught and f naught bar, something like that, okay? Then you take the closure. That is precisely this. That is precisely the C of sigma. So similarly, the T also should satisfy the whole same thing. T is just a self-adjoint element. You have to take the polynomial in T, then you take the closure. That's all, C star closure. Okay, this is fine. I mean, you will not get f naught star. I mean, you will get polynomials in complex numbers. Okay, you have to take polynomials in complex coefficient. Is this clear? The uniqueness is clear because it is determined by this. Because it's a homomorphism and this algebra A is generated by this f naught, and it will map to the algebra generated by the C-star algebra generated by this T. Okay, you take the polynomials in T, complex polynomials in T, and then take the closure in the norm. It will just map onto that. Okay, it's fine. Okay, I assume so. I don't see your faces. Whether if I see your faces, I can guess whether you have a problem with that or not. Okay. So we have proved the first part. First part says this: there is a unique representation. I mean, there is a representation. That we have to prove is we define it by taking polynomials to polynomials in T, and then prove that it's contractive. Then we get a representation, and it's unique because f naught generates the whole thing. Now we want to prove the other way. Suppose we have some representation, some arbitrary representation. Conversely, suppose pi is a representation from here to b of h. Okay? Then f naught satisfies this. F naught star, f naught bar equal to f naught. Because f naught t equal to t. Okay? And sigma is contained in real line. Okay? So f naught bar equal to f naught. So this implies pi of f naught star. I mean, pi of f naught star equal to pi of f naught bar, which is equal to pi of f naught, okay, which is equal to pi of f naught. So pi of f naught is self-adjoint. Okay, self-adjoint. Now we want to consider the spectrum of this. We want to consider what we want. The spectrum of pi of f naught is contained in sigma. That's what we want to do. Okay. Okay. Now the spectrum sigma of pi of f naught is contained. So we defined the spectrum for a general C-star algebra. Okay, I mean, if x is lambda is in the spectrum of x, if x minus lambda is not invertible in the C-star algebra. Okay, this is contained in pi of sigma of f naught. Right, f naught is a function, but it's an element of a C-star algebra. So you can talk about spectrum of f naught. Okay, this is all those lambda such that f naught minus lambda is not invertible. What does it mean by it's not invertible? Something is not, f naught is not invertible. As a function, something is invertible if the range does not contain 0. Right? The range contains 0, then it is not invertible. If and only if some function f on some set is not invertible, if the range is does not contain 0, you can make sense of 1 by f, and then you can multiply by 1 by f, and you get an inverse. Okay. So if the range, similarly, if a range has a 0, I mean, if a range does not have a 0, you cannot do that. And you can precisely, if the inverse exists, then the range does not have a 0. It's an equivalent thing, sir. Okay. So sigma of f naught is nothing but f naught of cis, which is this. Okay. Sigma of f naught is equal to this. Is equal to this. F of this. Okay. F naught, sorry, what I want to say is lambda, it should not be equal to 0. What I mean is the following. F naught minus lambda is not invertible. Means F naught minus lambda has to be, there exists a t such that F naught t, F of t minus lambda equal to 0. This implies there exists a t such that F of t equal to lambda. This is equivalent to this. Okay? F of t equal to lambda. So this is implies this is equivalent to saying lambda is in the range of F of x. If you take any function, okay, then F minus lambda is not invertible if and only if lambda is in the range. Or you say a function F is invertible if F does not vanish. Okay? So F naught minus lambda, if F minus lambda is not invertible, if F minus lambda does not vanish. That is equivalent to saying lambda is not in the range of this. It's not invertible, lambda has to be in the range. Okay, this is fine. So we have proved that if you have any representation, then pi of F naught is self-adjoint. That is clear. And then the sigma of pi of F naught is contained in sigma. Okay, this is fine. So these are the concepts we should we will be using it again and again. Okay. I hope the proposition is fine. It's fine.
Yeah,
Okay.
it's fine.
Okay. Okay. So now we want to define a special kind of representation, which is called, how much time? I have half an hour. Definition. Okay. So a representation by from A, we always assume A as a C-star algebra, A to B of H, and we will be considering the representation of C of sigma. Okay, by from A to B of H is a representation is cyclic if there exists a xi or xi naught in H such that you apply pi of x xi naught. Okay, this should be total, or you can, but it's a vector space anyway, so this is dense. Set x is dense, or closures. You don't need to take span, but it will be, because it's already a vector space. It's closure equal to H. Closure of the norm topology of the Hilbert space. So it just says that you have a single vector. If you act that representation on that pi of x on this xi naught, so you get a vector space, and that vector space is dense in H. Okay, its closure is this. So this just say pi of x xi naught. There exists a single vector such that this is, that is dense. This is the representation. So now let us see a cyclic representation of C of sigma. Okay. This is proposition. So let sigma. So are we using only? Let me use this. Are we using only sigma being sigma is an R or something? I think this is true for any sigma. Let's not able to see. So if sigma is in, we need anything like no, we don't need. Sigma is in C. Okay, I take it in C. Let's see if there is a problem. C. Okay, there is nothing to do with self-adjointness. Sigma is some subset of C. Okay. Okay. Then and mu is a finite measure. It's a compact. It's compact. Of course. It's always important that it's compact. Okay. Mu is a finite measure defined on Borel subsets. Borel subset of sigma. Okay. Then so we can if whenever we have a measure on defined on the compact set, then we can define the multiplication representation. Then pi mu of f acting on G equal to Fg. Okay, this defines for all f in sigma and G in L2.
So for all F belonging to C sigma, you meant?
Oh, yeah, correct. Good. So you are there. Okay, pi mu of f acting on this, G is there, is a representation. Is a cyclic representation. Representation with cyclic vector. That vector xi naught is called cyclic vector. Okay, this vector is called cyclic vector. With cyclic vector G naught, which is just G naught of G naught with G naught of t equal to 1 for all. We defined an f which is the identity polynomial, f naught of t equal to t. This G naught of t equal to 1. This is the identity element of the sister algebra C of sigma. So this is first one. So if you take the multiplication representation, given any measure mu, you take the multiplication representation, that's a cyclic representation. That's what this says. With cyclic vector, the identity vector. I mean, this G naught t is considered, because it's a finite measure, this constant function 1 is in L2, okay, because it's a finite measure. So, and that 1 is a cyclic vector. Okay, that's what this is. This one, G naught, is in L2. Okay, L2 of mu. Okay, so second thing is, suppose pi from C of sigma to B of h be a cyclic representation, be any cyclic representation, be a cyclic representation. Then there exists a finite measure mu on sigma. I forgot to say, let me say, such that pi, so let's call this pi, we called it pi mu, no? Pi and pi mu are unitarily equivalent. I will define what it is. Forgot to define. So this is definition. Two representation, pi 1 from A to B of h1 and pi 2 from A to B of h2 are said to be unitarily equivalent. If there exists a unitary u from h, this is h2, h1 to h2, okay, such that this intertwine those two representations, such that you can take u, you can take pi 1 of x in u star. So the u star is an operator from h2 to h1. Now pi of x1, pi 1 of x acts on h1. Then you apply u, you will get an operator. It will land up in h2. So this is an operator on h2. So which is pi 2 x. Okay. So if this happens, then we say two representations are unitarily equivalent. So pi 1 and pi 2 are unitarily equivalent for and such that I mean this unitarily equivalent as something more. It takes the cyclic vector to cyclic vector. Okay, maybe I will write the whole thing again. This is the definition of thing. So that is, there exists a unitary operator u from that whatever the case. You have an arbitrary representation, okay, of C of sigma. Then you have something from here to L2 mu, okay, such that u pi of x u star equal to pi mu of x. That's what unitarily equivalent means, and u of xi naught equal to that g naught. G naught 1 is 1, okay, where psi naught is the cyclic vector for pi. Okay. So if you have an arbitrary representation pi on some Hilbert space H, which is cyclic, then there exists a measure mu such that that representation is unitarily equivalent to this pi mu, and it takes that the unitary takes that cyclic vector to this cyclic vector. Okay, that's what this is. So these are the two statements. Then there is a third statement. I was saying that L infinity is actually a closure of C of x. Okay, I was saying that. So here, that's what I'm just making it precise. Okay. Further, there exists this is this is something to do with 1. Okay. Maybe I will write the whole thing. Mu be a measure, finite measure on sigma. Okay. Then there exists a pi mu tilde from L infinity x mu. This is also a sister algebra 2b of h, such that pi tilde mu restricted to C of sigma is the original pi mu which we defined, the first statement, pi mu. Okay. And it satisfies the following. And further, it's an extension of pi mu. Further, if Fn is a sequence contained in L infinity, and F is also in L infinity, such that norm Fn supremum of n is less than or equal to infinity, less than infinity, not less than or equal to, less than infinity, and Fn converges to F mu almost everywhere. Okay, then pi tilde mu of Fn converges to pi tilde of F strongly. We define the strong topology, you remember, some T lambda x converges to Tx, then T converges to T strongly. Okay? It's a point-based convergence. It's not norm convergence. It's not true for norm convergence. The point is, the C star algebra with the, when we take the C of x, when we take the C of sigma, we define a representation. That representation is norm continuous. Okay, it's norm continuous, and if you have Fn converges to F in norm, in the C of x norm, then pi of Fn converges to pi of F in the norm. But here it's not true for the L infinity. Here, if you have a convergence in L infinity, okay, then this, no, here that is true. Sorry, that is true also. No, because it's C star algebra, that is anyway norm continuous. But it also preserves the strong continuity. So that's what I want to say. Sorry. This is something more. You take the strong convergence. Suppose some Fn, you have Fn and it satisfies this condition. Supremum, it's uniformly bounded in converges mu almost everywhere. Then pi mu of Fn converges to pi tilde of, these operators, pi mu tilde of Fn converges to pi mu tilde of F. Okay. Any doubt in these three statements? We have made three statements. Okay. So the first statement is, you take a compact subset of complex number and you have in some measure mu, then you define the multiplication representation with respect to that L2 on L2 mu with respect to that measure. Then that's a cyclic representation. Okay, that is with the identity as the cyclic vector. So that is the first statement. Okay, so let me prove. Okay, so we have sigma contained in C, and we are considering C sigma. Okay, and mu on this. Now we have defined pi mu. I don't see anything to prove here. Pi mu of F acting on G. So that G is an L2 mu. Okay, pi mu acting on G equal to Fg. Then it is clear that the L2, if you take the integral Fg square du is less than or equal to norm infinity square integral G square du. Okay, so I mean, it is this is infinity now, L infinity now. But that doesn't matter. We have a representation. This is a representation of the C-star algebra. This is clearly, so this is a bounded operator. Okay, pi mu f is bounded. Is a bounded operator, right? Norm of pi mu is less than or equal to norm f infinity something. It will be equal. I will come to that. Okay, pi mu f. I mean, it will not be equal to the C norm, the continuous norm. That is something maybe greater than that. See, if you take the norm f infinity of the C of x norm, that is one such m which satisfies that condition for the L infinity, the essential supremum. So the L infinity norm with respect to some measure will be less than that. Okay. So, but we don't need all that. We want to say that pi mu f is bounded. That's enough. So this implies
like pi mu f, isn't it automatically bounded because we have C-star algebra on both sides?
No. Pi. We have to prove that pi mu f is an element of B of x. That's what I have proved.
Okay.
It's automatically that it's a representation. The representation is continuous is automatic. That's what I'm saying.
Okay.
That is automatic. But we have to prove that it lands up in pi B of h. For that, we have to prove that it is a norm. I mean, pi mu f
yes.
is a norm. Yes. That's what we are doing. Okay, so pi mu f is in B of h. Now it's a proper representation. The representation, I mean, when we consider C-star algebra, we don't have to prove the continuity. It's automatic. It's contracted. Okay. So now this gives a representation. Pi mu f, this gives a representation. Okay. And we know that C of x, if you take any C of sigma, is contained in L2 sigma. I mean, this is not the, I mean, this is a, see, L2 is a equivalence class, but you take the equivalence class of those functions. Okay. But if two functions differ, then they are in different equivalence class. I mean, and this is dense. We have proved in the last course. So if you take G naught, then C of sigma, if you, I mean, pi of A acting on G naught. You understand what I mean by that. Pi of G naught. This is just C of sigma acting on G naught. This is just C of sigma. Contain, I mean, as functions, possibly the equivalence class. You have to consider the equivalence class contained in L2. This is dense. Okay. So this implies G naught is cyclic. Okay. Is it okay? If you want me to explain, I will explain. Is it okay with everyone? You take the constant function 1. Okay. If you apply f on 1, if you multiply f on 1, you get f, of course. Okay. So you get all the continuous functions. As the, I mean, what, see, the cyclic definition is this. You have a vector z naught. That is, yeah. This is the definition of cyclic vector. Pi of x, z naught. This is dense. But here you are taking G naught, which is the constant function 1. If you apply pi of f on this, which is just multiplication, so you get f. So that way you get all functions, continuous functions. But then continuous functions are dense in L2. It is dense in all LP. In the LP norm and in the L2 norm, which we have proved in the previous course. Okay. Yeah, I think I proved, yeah. I mean, it was not in the presentation, I proved it sometime. Okay, so because of that, I proved it after some presentation, from one presentation. Okay. So because of that, pi mu is cyclic representation. So this is a cyclic vector for pi mu. Is this okay?
Yes, sir.
Okay. Okay.
Yes.
So this is a cyclic representation. Now I want to get the converse. Second is the converse. So suppose pi is a representation to B of h, is a cyclic representation. Okay. Then I want to get a measure such that this pi and that pi mu are unitarily equivalent, and that unitary takes the cyclic vector to cyclic vector. That's what I want to do. Okay. So what I do is the following: define phi of x for x in A, define phi of x equal to, you take the pi of x, okay, with be a cyclic representation with cyclic vector. That's Xi naught. Okay, you take this pi of Xi naught, you take this, you take phi of x equal to pi of x Xi naught, Xi naught. Okay, so phi is linear because the inner product is linear on C of this. Okay, linear functional on this, and it is clearly bounded because inner product is, I mean, because of Cauchy-Schwarz inequality, of course. Mod of phi of x is less than or equal to norm of phi of x, norm Xi naught square. I mean, this Xi naught you can take it to be 1, norm 1. Okay, we always take Xi naught equal to 1. I mean, if you take some Xi naught, you divide it by the norm, you get a unit vector. Okay, so we say it's a unit vector. That is the definition. Norm Xi naught equal to 1. You can take norm Xi naught equal to 1. Okay? You can just divide it by the, I mean, you can divide it by some constant. You can. It's happening. Yeah. So this is not there. Okay, so this implies norm phi of x, which is less than or equal to phi, which is less than or equal to norm x. Okay, right. So this implies phi is bounded. Phi is bounded. Okay, if Xi is, I mean, it depends on Xi naught square. I mean, if Xi naught is a unit vector, then phi is norm phi is less than or equal to 1. Phi is bounded. Norm phi is less than. Okay, phi is bounded. We claim that phi is a positive functional, positive linear functional. We want to use the Riesz representation theorem, which we proved in the last course. Phi is a positive linear functional. That is, if f is positive function, then we want to prove this. So claim phi is positive linear function. We proved in the last course the Riesz representation theorem. Every positive linear functional is given by a positive measure. That is, if f is greater than or equal to 0, then phi of f is greater than, the number is greater than or equal to 0. But that is just clear. If f is greater than or equal to 0, take f, the square root exists. The function square root f power half exists. Okay. Now pi of f, phi of f equal to pi of f by definition. This is this, but that is equal to pi of f power half because it's positive. And f power half is a real valued function, so its bar is same as the bar. Okay, but this is equal to pi of f power half, pi of f power half. Okay. But then this is its own star. Okay. Xi. Okay, because f power half is a positive function, pi is a representation, so it takes self-adjoint element to self-adjoint element. So pi of f power half is a self-adjoint. So this is equal to norm of pi of f power half Xi naught square, which is greater than or equal to 0. Okay. So if f is positive, then pi of f is positive. Phi is a positive linear function. So by Riesz representation theorem, there exists a measure, positive measure, not complex. I mean, every linear functional, every bounded linear functional is actually given by measure. That's what Riesz representation theorem. But we proved it for positive linear functional. There exists a positive measure on this, finite positive measure on this, such that it's a finite. I mean, it's a complex measure. It's also, I mean, it's a total variation is anyway finite, so it's a complex measure. And in particular, when the Riesz representation theorem actually says that if you have any linear functional, bounded linear functional on C of sigma, it is actually given by a complex measure. So a complex measure, total variation measure is finite. So here we have a finite positive measure. So its total variation is same as this measure of the whole set, which is finite. So by Reed's representation theorem, there exists a positive finite positive measure on this, such that phi of x equal to integral f d mu. Okay, integral d mu. Sorry, phi of f. Okay, I have used x, but it's okay. It's instead of x, I used. Yep, I mean I should have used f, but I used x. That's okay. Okay. Now this is equal to nothing but pi of f psi naught, right? This is same as this. Okay. Phi of f. Now you define unitary. U from h to L2 this mu. That's what we want to do. We want to see we have an arbitrary representation, arbitrary cyclic representation. For that, we want to get a measure mu, which we have got now using this representation theorem. Then we want to prove there exists a unitary between the Hilbert spaces which intertwine these two representations. That's what we want to prove. Okay, so now we have a unitary between h to L2 mu. So we know that it's part of the proposition that it takes the cyclic vector psi naught to f naught. G naught. G naught is the constant function model. So we know that. Okay. Now we know, so that's right. Then we define u of for any f. So this is defined, and u of psi naught is this, and define u of pi of x psi naught equal to pi mu of pi mu of f g naught, which is actually equal to f. Okay, f in L2. I mean L2 in the equivalence class you will, but let us just like this. Okay, I'm just defining it like this. Pi of f is psi naught equal to this. I mean, this is not defined on the whole space, but this is defined on this. Now I compute the inner product. Compute. So pi of f1 psi naught, pi of f2 psi naught. Okay, that is equal to pi of, you can bring it here as pi of f2 star, which I take it as f2 bar, which is equal to pi of f2 bar f1. Okay, psi naught. We can write it like this. But this is equal to phi of f2 bar f1. Okay, and that is equal to phi of f2 bar f1. So we know that that is equal to f2 bar f1 d mu. That's how, I mean, we got a measure mu which represents this phi. Okay, like this, and that is equal to, I mean, that is the inner product between f1 and f2 in L2. Okay, but that is same as pi mu of f1, if you wish, on g naught, pi mu of f2 g naught, because that's just the identity in L2. Okay, so this implies whatever the unitary we have defined, it's not unitary. Whatever the map function we have defined, which is defined on this set. Okay, this implies this u defined on this set, pi of x psi naught, this set, maybe f in C of this, preserves the inner product. Okay. If you remember in the previous course, I said that if you have a subset S contained in H1, okay, and you have something H2, define U from S to H2, which preserves the inner product. Then it extends to, and if S is total there, okay, then it extends to a unitary on the whole space. This lemma, it's asked in the exam also, which is very easy, but it's very fundamental lemma. So which is asked in the exam also. So this implies U extends. Because since phi of f xi naught f in C of this is dense, that's the definition of cyclic representation, is dense in H, U extends. And U preserves the inner product. U extends to a unitary map, to a unitary on H. And the range is also total there. So it has to be it has to be onto. This part is clear, which we have discussed in the previous course. And this was a question asked in the exam also. If you have a total subset or dense subset, okay, where you have define a map, you don't need to even verify its well-definedness or even linearity or something. If it preserves the inner product, it will automatically follow. All these things automatically follow. If it is defined on a subset, so this is the nice thing about that. If you define a map, see if you have a S1 contained in, S is enough, S1 contained in H1, and you define a map from US1 to H, such that US1, US2 equal to inner product S1, S2. Okay? Then this U extends to a unitary. You don't need to verify anything else. Well-definedness will follow. You please do this exercise if you haven't done that. Okay? If you have doubt, you ask me. Then well-definedness will follow, and it will automatically be linear, and you get a unitary defined on the whole of H1. And if U of S1 is also total there, in the sense that its span closure is H2 or something, then it's an onto map. Then it's a unitary. Otherwise, it's an isometry map. If that is also total, then it's a unitary map. Okay, this we discussed in the last course. So because of that, we have this unitary. So now we can see that this defines. Now it intertwines that. That's what we want to see. So now we want to talk about U. Now U pi of f U star, okay, acting on. So this is a map. U pi of f U star is an operator acting on L2 mu, because U is a map from H to L2 mu. So U star is from L2 mu to H. So it's acting on L2 mu. So you take some function f. Instead of function f, I take this kind of things. Pi mu of f G naught. So let me call it H. H of G naught. That is equal to U of pi of f. U star of this is going to be pi of H xi naught. That's how the U is defined. That is equal to U of pi of f, pi of H xi naught. Sorry, pi of H. This is the representation. Pi of f H SH xi naught. But then by definition, this is pi mu of fH xi naught. But that is just pi mu. That is just pi mu. That is just pi mu. What have we got? Pi mu, which is just the pi mu of f acting on pi mu of h. So these things, I have just verified that U of pi of f U star is equal to pi mu. As operators, it's coincides on these vectors. Okay, so it's a dense subspace, so it is as operators they are same. This is an operator. This is an operator. These two operators are same. It coincides on the lim subspace, so they are same. Okay, so that's what I verify. It's fine. So I have
Yes.
passed through the 6:30 is over, so I will prove the other part tomorrow, the L infinity part, so that I can recall the whole thing and we can go through it again. Okay. So it's fine. If you have doubt, you can ask me, or you can ask me in the next class also. Okay, I will end the session.